Good morning, students. Today I'd like to talk to you about the Pythagorean theorem. The Pythagorean theorem will help us determine the side lengths of right angle triangles that we do not know. The triangle must be a right angle triangle, and because of that, we're able to do some really interesting things. So the first thing we want to do is, what defines a right angle triangle? Well, it's quite simple, really. We have a right angle. Now, when we draw in the right angle, you'll notice that there's a point here. The point points to the longest side, and that is called the hypotenuse. Okay? We always want to know where that is. In work with the Pythagorean theorem, the hypotenuse we're always going to call C. So you want to put that in brackets. If we look at the next one, same thing here. Okay? Find the right angle, draw across. This is our hypotenuse. And again, we are going to label it C. This will be useful in a little bit. This question says, what is true of all hypotenuses compared to the other sides? And it's quite straightforward. The hypotenuse is always the longest side. If we keep that in mind, everything will work out for us. We just have to be able to identify the right angle, then use it to find the hypotenuse. So let's try that here. If we have, we'll go to green, and if I look, here's the right angle. There's the hypotenuse. So we would label that C. Here, in this triangle, we have a right angle. And there it is, it's pointing, there's C, and there's the right angle here, and it's pointing at C. We always want to know where the hypotenuse is. When we put the formula together and we utilize it, knowing which one is C will help us reorganize the formula effectively to get what we need. So the Pythagorean theorem looks like this, that if we were to use cubolinks and take a right angle triangle, and here's the right angle, if we just look at it real quickly, right inside, and it's pointing at the hypotenuse, you'll notice that B, the side length here in that triangle, so if I was to draw that triangle real quickly without the labels, it's a right angle triangle, and if you notice, this length is 3, 1, 2, 3. This length is 4, okay? And this length is 5. So how does this formula here work for us? That's what we're going to work out. How would we use 4 and 3 to get 5? Same thing here. When we look at this right angle triangle, again, we have our right angle inside. It is pointing to C. And it's saying to us, okay, I know one side length is 6. I know it's 8. How will I use them to get the missing value? So what you can do, and we're going to set this up right now, it doesn't really matter in this situation which is A and which is B, but we'll just go and say that A is going to be 6 and B will be 8, okay? And then C we don't know. Now the formula states A squared plus B squared equals C squared. I would encourage you to write it like this: C squared equals A squared plus B squared. The reason I want you to write it like this is I think you'll find it easier to use, especially with your algebra skills that we worked on earlier this year. This will work in a format a little bit smoother for you. So let's plug it in. We don't know what C squared is. We don't know what C is, but we know that A is 6. So it's going to be 6 squared plus, and B was 8, and that's going to be squared. So order of operations, we take care of the squaring. So we have C squared equals 6 squared is 36 plus 8 squared, which is 64. Now we get C squared equals 100. Now if you look, 100 does not fit. If I put 100 here, that is not a reasonable estimation for 6. That doesn't make any sense. So there's a step missing that we need to deal with. And if you look very carefully, you'll notice that C is squared. To get rid of the square, we can do the square root. C square root of C squared equals the square root of 100. what we do to one side of the equation, as you know, we do to the other. So now we have C equals 10. And that is definitely a more realistic answer for C. And that is how you use the Pythagorean theorem. Next, let's take a look at what we had on the previous page where we had 3, 4, and we're trying to find the value of C. Here we have cubolinks have been provided, and we can utilize the cubolinks if we want. We know that this side length is 3. We know this side length is 4. And this one is 5, but we need to prove it using the theorem. So let's go ahead and do that. As I mentioned to you, use this formula here. I find that this will, the way it's organized is better. Put C on the left and then equaling that. So if we do C squared equals A squared plus B squared, we can then substitute in A. We'll say that A is 3, and we'll say B is 4. So 3 squared plus 4 squared, which gives us C squared equals 9 plus 16. C squared equals 25. Now, as I had mentioned to you previously, if I come up here and I say that this is 25, that doesn't really jive, because if I have 3 and 4, I wouldn't expect that length to be 5. Even with proportional reasoning, that doesn't really come out well. So again, I've missed the step, and what I want to do is I want to square root. Sorry. What we want to do is we want to square root C squared. So the square root of C squared equals the square root of 25. And if we do that, we get C equals 5. And 5 really does fit in here, and you can see that it works with the cubolinks. So we can show it geometrically. There's your 9, right? If we go over, there's your 9. That comes out here. Here's your 16. That comes out here. And then when we play it out, here are your 25 cubes. That comes out here. But we want to get down to the root, so that's why we square root it down to get to our value. What would you do if the hypotenuse side was given to you and you were asked to find one of the other side lengths? So if we were to draw on the hypotenuse, we can see that it's right here and that it's 13. We have A, we don't know what A is, and we have B, which is 5. Our regular formula would be C squared equals A squared plus B squared. But if we're missing a side length, we can rejig that and make it A squared equals C squared minus B squared. And if we're missing B, it could be B squared equals C squared minus A squared. In this instance, we can go with this formula here. That will work for us. So let's go ahead and plug it in. We would use A squared equals C squared minus B squared. A squared equals 13 squared minus 5 squared. A squared equals 169 minus 25. A squared then equals 144. It won't make a lot of sense for us to plug this in unless we square root it. So let's go ahead and square root it. Square root of A squared equals square root, excuse me, of 144. A equals 12. And that fits. This side length here is fairly long, but not longer than the 13. So the hypotenuse is still the longest, and we found the missing values. In this problem, Don is building a loft in his garage. The ladder he is using extends 10 meters. So we can actually right away put 10 meters here for the ladder. And it says the loft is 8 meters from the floor. This is 8 meters. How far away from the wall should he anchor the ladder? That means this part here is unknown. There is a right angle. It does push out to the hypotenuse, but it's this red line that we've got to figure out. So if we call this C, and we call this A, then B is what we're going for. So let's go ahead and use our formula. And we would start with B squared equals C squared minus A squared. B squared equals 10 meters squared. Now, if you know the measurements, use them in the formula so you don't forget to put them at the end. Minus 8 meters squared. And we should put these in brackets just to make sure that we get the squaring done properly. So there we go. That means B squared equals 100 meters squared minus 64 meters squared. B squared equals, and we subtract those off, we get 36 meters squared. We then can square root B squared and then do the square root of 36 meters squared. We're left with B equals 6. And that does fit with what we want. So here we could say, therefore, Don should anchor the ladder 6 meters from the wall. And I realize I needed to put the units in there as well. This last question is quite unique. It looks very complicated. And the question says, excuse me, determine the perimeter and area of the following figure. When I first looked at it, I wasn't really sure how I'd approach it because I definitely need to find this side length right there. And I was thinking about the area and thinking, I got to chop this thing up and it's going to be 3 or 4 different shapes and it's going to be quite complex. But then I realized there's a way to do this. If I take that line there and I come across, I can make a right angle triangle. This would be C. Now, here could be A. It's 8. It's already telling us. Now, this says 4 centimeters here and 4 centimeters here. And the whole thing is 16. That means that this is 8 centimeters. So I can use the Pythagorean theorem to find this missing value. So let's go ahead and do that. If I do C squared equals A squared plus B squared. So we already said A would be 8 centimeters. And this can be B. So we have 8 centimeters squared plus bracket 8 centimeters. And then square it. C squared equals 64 centimeters squared plus 64 centimeters squared. C squared equals 128 centimeters squared. And if I go to square root that, we are going to get our missing value. So we have 128 and we end up with 11.3. So C squared, square root of C squared equals the square root of 128 centimeters squared. We are left with C equals 11 and 3/10 centimeters. Now we can actually go ahead and find all the pieces and put it all together to find the perimeter. We know that P equals sum of all sides. So let's start here and work our way around. We'll have 12 centimeters. The bottom is 16 centimeters. This side would be 12 because it matches up with the other. We have 4 up top. We now have the 11 and 3/10 centimeters that we found using the theorem, and then the 8 here, and the 4 at the very top as we've gone all the way around. When we add that all up, we end up with 67 and 3/10 centimeters. So that's our perimeter. Now the area is a little bit different. Again, I looked at this for quite a while trying to figure out how I would do it, and then I realized I could find this rectangle that is 12 by 16, and then subtract out this triangle in the middle. So I would be able to do the area of the large rectangle, subtract the triangle, and what's left should be the area of that complex shape. So if I do A equals length times width, I can do 12 centimeters times 16 centimeters. That will give me 192 centimeters squared. Now the triangle is kind of easy because it's base times height. We know it's 8 and 8. So A equals base times height divided by 2, which equals 8 times 8 divided by 2, which would be 60, it should be centimeters and centimeters. So that would be 64 centimeters squared divided by 2. And when we divide that by 2, we end up with 32 centimeters squared. If I subtract 192 subtract 32 centimeters squared, I end up with 160 centimeters squared, and that would be the area of the complex shape. And that was our goal all along. So a couple learnings with this question. Number one, think about what strategies you could use. Use your formulas and break things down piece by piece.